We now have Professor Ken Kreutz Delgado. He's an emeritus professor in the ECE department at UCSD and a life fellow of IEEE. Previously, he has worked as a researcher in intelligent robotics at the NASA Caltech JPL. His research interests include robot kinematics and control, sparse signal processing and dictionary learning, EEG and fMRI brain imaging, and implementation of machine learning algorithms for efficient IoT and edge-of-the-cloud applications. Incidentally, he was on my PhD committee.
So I'm also going to talk about the of Bhaskar's life, but since the advent of the paper, multiple measurement vectors, we're going to do a little archaeology here, because Bhaskar did start with his focus algorithm, but Bhaskar doesn't stop. Bhaskar keeps moving. I remember when Bhaskar came to me and he said, Ken, do you know that no one knows how to solve these inverse problems in general? And I said, oh, that's got to be a solved problem in linear algebra. He said, no, it isn't. So in other words, he saw the opportunity from this interesting research he did with Irina and George, and he said, there's more, it's deeper, we have to do more. So he did. And so I'm going to talk a little bit about how we moved that basic algorithm into multiple measurement vectors and moved into sparse Bayesian learning, which is a very powerful modern way to address the problem of finding sparse solutions. Let's see how I move this. How do I move this? There we go. Oops. There we go. This is dense slides. I'm just going to talk a high level of ideas appropriate for understanding the importance of that paper. Because the truth is, the focus algorithm is a useful algorithm, but it has been superseded. And it's been superseded by a lot of results that have come out of Bhaskar's lab. So I want to make that clear. I'm going to motivate it with the real-time EEG signal processing problem. If you look here, I'm going to talk to this slide, but we talked about MEG before. That's what Ethan spoke about. And here I'm going to talk about EEG. What happens, that's a really hard problem. That's real-time EEG signal processing. People are interested in this because people want to understand your cognitive state as you walk around for a variety of reasons. The problem is hard. You have y equals hx, where h is uncertain in this situation with the EEG framework. It's very wide, so it's a very underdetermined problem. The signal-to-noise ratio is quite high or large. You need to know that matrix H. And getting that matrix H is hard for physically meaningful problems, such as understanding EEG. There are ways to do it, but it's going to be very noisy. Or you might have to learn it, so it's going to be very noisy. So your model is going to have a lot of error in the model. Okay. There'll be artifacts, is what they call it in this domain. Solving the inverse problem then is hard. It's common to use L1 norm. This has been done by groups out of UCLA and Stanford. I'll talk about that. But working with Bhaskar, we looked at more general sparsity measures, and that was of use. And we started understanding what you get from using more general sparsity measures. You can ask for uniqueness of solution, but uniqueness isn't always the right answer. Okay, focus will give you a unique solution, and we'll talk about that. But the reality is, mathematical uniqueness is nice. But if someone gives you a two-norm solution, because they imaged your brain, you'd like to ask the surgeon before he drills in your brain, if that solution is more than just mathematically nice, is that where the lesion is? And the lesions are localized. So you really do want the ability to sparsely localize these things before you go under the knife, right? So we're dealing with model uncertainty, a lot of noise, there's signal corruption, the H matrix is poorly known. This is a hard problem. So with this paper, I'll go back to the beginning, multiple measurement vectors, this use of multiple measurement vectors, which I'll explain, is a powerful regularizer that can help you zero in to the right answer. Nothing's perfect, of course. There's always risk associated with it going under the knife. But we want to get as good as we can, and we want to continually improve our answers. The paper up there, the sparse solutions and linear inverse problems with multiple measurement vectors, I'll refer to it as paper 4. So paper 4 proposed the use of the multiple measurement vectors and how to incorporate it into focus, but I'll talk more generally about how it's useful regardless of the sparse solution algorithm you're using. It's a general approach that's used in modern times, even when people have moved beyond focus as an inverse solution solver. So the multiple measurement vectors are interesting and useful. They continue to be useful. They're currently greater than 1,600 Google citations of this paper from 2005, almost 20 years ago now. So here's a motivational example. And this is actual work being done at the Schwartz Center for Computational Neuroscience here on campus, done by students who've been trained by Bhaskar and myself, ECE student graduates who work in the Schwartz Center. Okay, the point is in real time, we want to collect signals on the scalp of a human subject. We take this multi-channel EEG. We then ultimately would like to understand, let's see if I can get this to work. Wonder why this is not, where's the, anyhow, you'll see those little bubbles up there, those balls. And what, oh, that's the one to use? Okay, thank you. Excellent, thank you. Okay, so what happens, what this is cortical activity on the surface of the human cortex. They've been isolated, and the different colors will correspond to the fact that, yes, the brain can turn on, and you can have this constellation of activities, but depending on your cognitive state, there'll be different arrangements of cortical activity. It's a different type of constellation of activity. So you'll see the different colors that talk about the potentially different ways your brain can be fired up. What we've done is we said, look, there's these activities on the cortex of the brain, and the cortex, that are received by electrodes on the scalp, and depending upon, say, basically dipole 1, they're little dipoles, dipole 2, dipole N. If dipole 1 fires, you see a certain activation pattern on the scalp that many electrodes pick up. In the old days, they used to think, oh, that's where the brain is turned on. But in fact, it's not necessarily clear. There's other parts of the brain that might be turned on, so you can get fooled. But basically, you sum up these activities with what you see, these basically eigen type of structures on the scalp, and you sum them up and you get what you see with the EEG signals. There's artifacts, and so we can add those. With these things that take you from the cortex to the EEG signal, these are figured out, let's call it L, the lead field matrix. They're computed for a given human being by taking an MRI image or something like that and using neurophysiological information to try to get a model for what these columns are. They're very poor. You could try to learn them using dictionary learning, which Bhaskar has done a lot of research on, or try to improve them using dictionary learning. You can also try to move the artifacts, which corrupt your EEG signal. That could be your heart pounding or your blinking. Okay, so all in all, what you wind up with is a bunch of cortical positions on the brain, little dipolar activities, and there can be thousands of them mapping to, I don't know, if a high density system for EEG could be 128 electrodes. Okay, so what happens, this is hard. We shouldn't be so surprised. It's really hard. Okay, those scalp signals we know are noisy and corrupted by artifacts. The lead field matrix is very poorly known, okay? Even if you knew that full matrix, its width is far, far larger than its height. So the inverse problem is highly underdetermined. We need to solve this ill-posed inverse problem for known H, and we need to understand these activities are localized in the brain. They're not spread throughout the brain. A two-norm solution is a maximum entropy solution under the Gaussian assumption. That means it basically assumes that everybody plays a part. These aren't max entropy solutions. These are very focused, localized solutions. To solve this ill-posed problem, there's a variety of techniques that have been devised, beginning with focus in, as we mentioned, in the 1990s. But a lot of good work has come out of UCLA and Stanford on compressive sensing. This focus algorithm, this iteratively reweighted least squares problem we just heard about, actually with some hindsight, we could see that it was actually used in the oil exploration industry, and geophysicists used it beginning in the 1970s and 1980s. So there was a history, but you had to know where to look. It was very unusual and unheard of for it to be done in biological domains, which made them very nervous. Okay. We moved to then what's called sparse Bayesian learning. In particular, a lot of activity from Bhaskar Rao's group basically led us to this new regime where we use the sparse Bayesian learning techniques, particularly in the Schwartz Center for Computational Neuroscience. And the Schwartz Center has software and tools that are used around the world. They have the most used laboratory of software tools in the world for EEG analysis, developed by many of our PhD students that came out of ECE department that have worked with Bhaskar and worked with myself. This is kind of unknown, I think, to a lot of us in ECE department, but it's absolutely true. Compressive sensing is, like I said, kind of almost classical now. We've got this really fat matrix. There's an infinity of solutions because it's got a huge null space. Of all those solutions, which one do we get? Well, we're saying we're in a domain where things should be localized because you're looking for oil, or you're a geophysicist and you're looking for what layers of the Earth correspond to maybe sources of magnetic fields or earthquakes or what have you. We're interested in lesions in the brain. Okay, so we want to regularize other than using a minimum 2-norm regularizer. The point is, you can look at these techniques, say with Candace and Tao or Donahoe and Alad, and they can give you conditions under which you get a unique solution. But a mathematically unique solution is not necessarily the physically reasonable solution. The noise, if you imagine there's noise, you can think of the noise as giving you the wiggle room to get a good answer, a better answer, the answer where you'd have the surgeon drill into your head. So we noise also as a cover for the fact that our model's wrong, okay? And so what we could do is impose constraints to try to guide the model in the right direction. But one of the things we could do is we could say, look, there are constraints that will hold collectively on an ensemble of measurements we take. And that's what the multiple measurement vector is all about. That the collective will talk to us and tell us something about the type of answer we're looking for. And if we went to a Bayesian framework, which is what happens when we go to the sparse Bayesian learning, this could be encoded in the form of a Bayesian prior. So the focus in sparse Bayesian algorithms give more solution possibilities, I should say. Let me go back up here. Go back here. What happens is lasso is these 1-norm solutions. You actually look for a 1-norm, an optimal 1-norm solution. The truth is focus looks at the case where instead of p equals 1, you have p less than 1, in which you give up the full norm properties, but it increases sparsity. And when you have the 1-norm, you get guaranteed uniqueness under reasonable conditions. And that's what Candace and Tao and Donahoe and Elad and others have spoke to. But the reality is that mathematically correct solution, that exact solution, what's going on here? Oh, there we go. That mathematically correct solution may not be the solution you really want. So if you take focus, which is a iteratively weighted least square solution, I'll talk about it, and you let p less than 1 up there, okay, p equals 1 gives you, basically the Candace Tao type of stuff, or Donahoe and Elad, you actually increase the pressure to go sparse fast. You do, though, in a way by collecting additional local minima, and that's what Ethan just spoke about. Now, it turns out that actually is good because experiments have been done that show that one of those is likely to be a good answer. Kind of don't know which one, so you need to be smart about it. But you can maybe be smart about it, again, by looking at the collective of solutions, and we'll talk about that. That's what the multiple vector is. The sparse Bayesian learning is another way to do this, and Pia Powell will talk about this. She'll talk about one of the students of Bhaskar that worked closely with Bhaskar, David Whip, that created some very powerful sparse Bayesian learning algorithms. In particular, what happens is that Pia is going to talk about these type 2 hierarchical or empirical Bayes methods. That's actually a hierarchical / empirical Bayes method. It's called type 2. And what happens versus type 1, this is type 1, you basically have here, I'm going to show you here. Here you have a prior on the solution that can shape the solution, but it's very rigid. This gives you more power to shape the solution. Let's see if I can get this. This gives you more power to shape the solution in a context-dependent way if you go one layer up. Okay, and you can get sparse solutions that are better fitted to the problem that the surgeon cares about. Okay. Now, this is out of Scott McKegg's lab at the Schwartz Center. This is actually using sparse Bayesian techniques that are quite recent. Reference date is 2020. And what happens, you see now we're at the point where we can actually see activity that's localized depending upon the context of the patient. So in this experiment, they said, oh, imagine fear, imagine joy, imagine happiness. And what happened is they could just take a bunch of data when somebody was fearful or a bunch of data when someone was happy, and they could see it collects. So, oh, here's all the happiness, and here's all the fear. So if they know the subject is in a given state, there's a fixed kind of sparsity pattern. And that's what the MMV is going to utilize. It says, when measuring the subject in a given cognitive state, we presume the activity pattern is constant. We then collect multiple observations when that condition is presumed to hold. And we'll call that a multiple measurement vector. So all these Y's were collected when the subject was told, be fearful. Then the activity pattern itself, though, is unknown. We just know they all have the same activity pattern, but we don't know what it is. So this is a very interesting type of constraint. And interesting enough, Bhaskar was the first person to have the insight to say, this is exploitable. Let's use it. Let's force this really ugly inverse problem with noise, and we'll give up an answer that's 100% best. 5 minutes? Okay. 100% best to basically get one that's better, because it's going to conform to the fact that a bunch of these guys want to be in the same activity pattern. Okay? So we're going to solve this in a way that we're going to force entire rows of the solution to be 0. Okay? That's what we're going to do. We're going to do this using, now, in hindsight, it's 2020, and we know machine learning. If you look at that paper and say, what did they do? In modern times, it'd say, oh, you just did block sparsity-based optimization. We satisfied this inverse problem subject to a constraint that you're enforcing block sparsity on that data for that given cognitive state. Okay? And there's some equivalent ways to write it. If you write it this way, one can apply iteratively reweighted least squares, and that just basically repeated linearization of this and solving, repeated linearization of this and solving it, and basically that'll give you focus. And that'll give you the M focus, the focus that uses the multiple measurement vectors. But the truth is, the take-home message is this approach can be used, the block sparsity-based optimization can be used regardless of the optimization procedure you commit to, even the modern ones that Pia is going to talk about. Okay? So here's a contemporary example in brain source imaging. This was in a NeurIPS paper of 2021, very advanced paper. And what they basically say is, look, there's a bunch of cognitive states that human subjects are in. There's G of them. And so what they do is they develop a very advanced sparse Bayesian learning method. And what they do is then they say, okay, let's use the type 2 Bayesian learning, the modern day jazzed up version of sparse inverse problem solving that started with focus. Okay, and they basically compared a variety of activation algorithms and showed that theirs did really good localization. exploiting this type of regularization of the collective behavior of sharing sparsity pattern. Okay? So my concluding thoughts are that paper from 2005 pioneered an important approach, okay, to stabilize solutions in these poorly known, poorly structured, poorly modeled domains by incorporating the tacit structural information that they share this sparsity pattern. This approach is now, we can say, oh, it's obvious now. It's 2022, we know machine learning. It's block sparsity. It was not obvious when it was first proposed. And you could argue that this paper was path-breaking in that regard. We just didn't use the right jargon, okay? That paper continued the pioneering investigations initiated by the Irina and Bhaskar's paper that Ethan just spoke about. But he didn't just stop there. Bhaskar mentored a series of talented students to produce powerful, hierarchical, empirical-based, type 2 sparse inverse problems that in many ways have superseded the focus class of algorithms that he first delved into. The contribution of Bhaskar and his students to sparse Bayesian learning and MMV-based algorithms continue to have seminal impact. In fact, just for this year to date, almost 20 years after its publication, that 2005 paper has already garnered 46 Google citations just this year. Okay. And for those who are interested, I'll provide a whole bunch of references. And that's my talk. Thank you.